All right, hello everyone. Today is July 13th. We are going to complete chapter 14 homework today. If we don't, we can always try tomorrow, but we'll try to get as much done as we can. So I have the PowerPoint slides open. Let me share my screen and we'll go on to it. And please note, I've noticed this with some students, they email me some questions. Sometimes we have different homework questions. And what do I mean by that? You may have pentane, I may have butane. So, pay attention to, there might be some subtleties that, you need to pay attention to. So with that, let's begin. All right, my mouse is not cooperating. Let me get this working. Oh, there we go. Question 1. It says select the vibrations that should be infrared active. You have 1, 2, 3, 4 choices. 5 choices. You gotta select the one with the, basically you're gonna be looking at the ones that have a hydrogen on it. So with the triple bond, if it has a hydrogen, it will be IR active. The CO carbonyl stretch will be IR active. There's gonna be one that has a carbon triple bond in the middle where there's no hydrogens. That's not gonna be IR active. We talked about that yesterday. We talked about this one where we have a CCl stretch, and that'll be IR active. And then trans-4 octene, that's not going to be IR active. So here's your 3 choices that are going to be IR active. You may have a different order than me, so you kind of need to pay attention to, what we just described. That's question 1. Question 2, we can do it on the same slide. It says, the calculator, I did bring my calculator with me. So for light with a wavelength of 9.6 micrometers, calculate the corresponding wave number. So, we're gonna have to turn micrometers into centimeters. It's no big deal. So we have, and you may have a different number here. You probably do have a different number than I do here. So, you need to pay attention to whatever number that you have. I'm gonna convert this into meters. Draw this better. So it's 9.6 divided by 10 to the minus. I'm not using a calculator for this. Hopefully I get it right. If I get it wrong, let me know. And I think I'm gonna have to divide that. So hold on. Okay, so then you take whatever your answer is, you take 1 over your answer. So, you may have a different answer than me. It's no big deal. And I'm going to get 1042. And this is per centimeters. Oh. Because your answer is in centimeters, so it's per centimeters. So like I said, you may have a different number than I have, but the process is the same. Question 3, we can put it on the same slide. Oh, it's not writing. There we go. It says which region corresponds to the stretching vibration of the NH bond. So I'm not sure if you have this same question, but if you do, it'll be found in the 3,500 to 3,300 range, whatever that corresponds for your answer. For me, that's region A. So that's what I have to put. All right. Moving on right along pretty good. All right, so let's go to question 4. Question 4 says, which region corresponds to the vibration of a carbon-carbon double bond stretch? So this is what I have. I have a compound like this. I do have some other stuff off of it, but they're just curious. They just want to know about the carbon-carbon double bond. So these are typically found in the 1600 to 1500 per centimeter region. And that will be region D for me. Region D, I mean, my first name starts with a D, or we can call it delta. So that will be question 4. So question 5, I'll put on the same slide. So I have 3-hydroxy-2-butane 1. So 3-hydroxy. I just have to select the correct spectra. So we have an OH stretch. If you draw this out, this will look like this. So we have the OH stretch here, and we have the carbonyl stretch. So we're kind of looking for that. So, your carbonyl will be 1740. This will be around 3530. Not a lot of hydrogen bonding going on with this then, because if there was hydrogen bonding going on, remember that OH stretch would be really broad. So we don't see a lot of that. That's okay. So you're going to select the one that had 3530 and 1740, and you're going to put a checkbox. So whatever option that is for you. All right, so that was 5. Let me take a look at 6. Let's just make sure I was on. Yeah, I was on 5. Yeah. So 6, we can even put this on the same slide. Says which compound matches this IR spectrum? They give us a whole bunch of options here. What we want to do is we want to see we have this And this will correspond to somewhere around 910. 990. And that has the, I should have put the hydrogens in there because that's what's going on. And we have this here around 1640. So this is going to be 1,5-hexadiene. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. There you go. That's what that is right there. All right, I don't see any questions. I guess we're going at a good pace for you then. Remember to check the homework due dates on Achieve. So if you are listening asynchronously, this homework is due July 20th. So when you work on the homework, it shows you the due date right in the top right-hand corner. So please get your homework done on time. I would just, if you're listening asynchronously, I know this doesn't really pertain to the synchronous students. It kind of does too. If you're listening synchronously, I highly recommend just to do the homework along with me. If you listen to it on your own time, I would have my computer out with my homework ready, and I'd be doing it along, as I'm talking through it. So that's just my best advice for you of how to get your homework done and not have to worry about the due date. Okay, so let's go on to question 7. Because the homework should be really easy points for you because we do it together. Is which compound matches the IR spectrum? So you see we have we have hydrogen bonding here. We see this large peak, around 3,400. So we know we're going to have some type of hydrogen bonding. If you don't see hydrogen bonding, just get rid of it. And then we see this, like kind of what we did last time at 910 and 990. On a real IR spectrum, you can blow this up even more. I know you can't blow this up as much on this, but when you get to an IR spectrum in lab, you'll be able to blow it up more. So this is going to correspond to 1-hexene real. I drew that kind of close right here. I mean, yeah. So you got something like that. We can put 8 on the same slide. So it says consider the IR spectrum of the unknown compound. Which compound matches the IR spectrum the best? And they give us 6 different compounds to look at, and we have a really sharp peak at 1685. So that's going to be telling us something, and that's going to correspond to a carbonyl peak. So we're going to select option F. So you have 2 phenyl groups here. It'll look something like that. On 9, it seems like we have the same options, but what's different is we do have some different peak shapes. The one we want to pay attention to is the one at 1725, and that would be coming from our aldehyde. So we are going to select option. We're going to select this one. That's option C for me. All right, let's go on to 10. It says we have this. We know we're going to see that triple bond with this right here. And we have a carboxyl group. So this will occur around 3,300. And everything is per centimeters when you're looking at IR spectra. And this OH stretch right here, if you imagine this here, this will occur around 2,500, 3,300. This will occur at 2,150, but it's not an option, so it doesn't matter. And this will occur around 1,700 to 1,725. So the only options we have are that one, and we are going to select this one. So question 11. Says IR spectroscopy can be used to eliminate possible compounds because of the lack of IR absorptions. That's true. Expected for key functional groups. Consider the IR data of an unknown compound. It says we have a very strong stretch is observed at 1,700, and only a weak stretch is observed at 3,000 to 3073. Is given the IR data, which functional groups can be eliminated? We kind of already talked about this, about the carboxyl group. So we're going to be able to eliminate that because we don't see anything in that area. So we're going to eliminate that. Because it's it. And that's because we'd see this stretch right here, somewhere between 2,500 and 3,300. We're not seeing that, so it can't be a carboxylic acid because it says it's only a weak stretch. If it was really an acid, you'd see some big broad stretch and it'd be large. And the amide comes around 3,500 to 3,300. We don't see that, so we're going to select these two options. So it says identify the functional group present in the compound. We do have some type of carbonyl group, but it's not a carboxylic acid because we're missing the 2,500 or 3,300. So we are going to select an aldehyde. All right, so let's go on to 12. Let's select the correct terms to complete each sentence. It says, so A, that's your base peak. That's assigned a peak of relative intensity of 100. B, the blank is the most intense peak. That's again the base peak, so this is going to be the same answer for B. C, the blank represents the original molecule. That would be your molecular ion peak. D, the blank could be represented a smaller charged fragment of the original molecule. That's going to be your base peak. And a radical cation. Blank is represented a positively charged species. E, you're going to select all of them. So it's 12, 13. So in this mass spectrum, which peak most likely represents the molecular ion? That's going to be the one furthest to the right, which would be 100. So you select that one. So that one's done. Let's go to 14 then. Says given the parent compound, draw the mass spectrum fragment that is observed at mass of charge 43. So they give us 1, 2, 3, 4, 5, 6, 7. They give us a 7 something like that. And they want us to draw something at 43. So let me think about this for a second. 12, 24, 36, 37, 38, 39, 44. 3. That's something that breaks off. And then we have, this will be our answer. So this is what you're going to observe at 43. So that's 14 done. All right, so let's go on to 15. It says which of the molecules will have an odd number of molecular ions. You're going to select the ones that have an odd number of nitrogens, so odd number of nitrogens, whatever that is for you. For me, this is going to be options 1 and 5. It could be different for you, but that's what I have to select. So that's 15 done. So we can do 16 on the same slide. It says I have a molecular ion peak at, let me see, 380. It says complete the formula, CnHY. So that's what we have to do. So M equals 12N plus 1 times 2N plus 2. And this is the mass of carbon. This is the mass of your hydrogen. This will be equal to 380. That's the number of carbons. So hydrogens would be equal to, just put it in this equation. What is that? 27 times 2 is 54. This would be 56 then. So we have that one done. All right, so let's go on to 17. So 17 says the mass spectrum of organic compounds shows the relative abundances to be 35.89 at M and M plus 1. So you notice the M plus 1 is your carbon 13 peak. Assuming the peaks are caused by carbon 12 and carbon 13, determine the number of carbon atoms in the compound. And it tells us the natural abundances of the carbon 12 and carbon 13. Remember, carbon 13 and carbon 12 have the same number of protons, but just different number of neutrons. So we're going to take 1.07 divided by 98.83 and get around 1. That's the first step. And the relative abundance, we're going to do some shorthand. Equals the natural abundance of carbon 13 over the natural abundance of carbon 12. And we already did this right here. Times the number of carbon atoms. So we have the relative abundance of the m+1 peak. So we're working on the left-hand side. And what is that? That is 2.71 for me. This is the relative abundance right here. This is your m+1. And then your m peak is 35.89. We take this to the other side. That means we're going to have to put it in the denominator. And this is approximately equal to 7. Question 17 now. Okay, so let's go to 18. It says, imagine that you're given the mass spectra of these two compounds, but the spectra are missing the compound names. Which peaks occur in one isomer, but not the other? That is, which peaks could be used to distinguish one isomer from the other? We have two isomers. Let me see. Break that apart. That's a 29. Let's see. 12, 14. Oh, 12 plus 12 is 24. 27, 29. So that would distinguish that one. Let's see which other one would this be a distinguisher. So the other one would be the 85, and that would be everything left over. So 29 and 85 is your answers. All right, we can even do 19 here. It says for the formula C6H14. I mean, you could, what is this? This is CnH2 plus 2n. I think that's what it is. So if you put a 6 in here, you get C6, and then you get the H14. So there's really not much going on with this. 1, 2, 3, 4, 5, 6. That's all this compound looks like. So you're going to select, so what types of unsaturation? So this is fully saturated. So the index of hydrogen deficiency should be 0. And it says what types of unsaturation might be present? There is none. So there is none. You just have to select the answer with no. But the equation is IHD equals 2C It's 2 minus h. There's no x and there's no n. And you divide that by 2. I mean, you'd have minus x plus n, but those are both 0. So 6 here, 14 here. If you do the calculation, we get 0. So we have 19 done. 19 or oh, we missed one. I guess this is 20. We'll do 19 here in the middle. It says select the compound that was used to generate this mass spectrum. You know, if you just calculate the molecular weights, you'll find that heptane is 100, and that's the only one. I mean, there is another one that is 102, but then, you know, 2,4-dimethyl pentane is also 100. But if you do the breakdown products, you'll see that you'll have 100 minus 15. Let me see. But we do see 29 and 30 and 71 in the spectrum, so that's why you're going to select heptane. So we have 18, 19, and 20 done. So that's 18, 19, and 20 all in this one slide. All right, we'll go to the next one then. That will be 21. We're going to use the same equation, IHD, index of hydrogen deficiency. We have C4H9Cl. So I'm just going to put in the numbers right away. This corresponds here. Minus how many hydrogens? 9. Minus X. In this case, we have 1 chlorine. Plus nitrogen plus 0, because we have no nitrogens, divided by 2. So what's 2 times 4 is 8, plus 2 is 10. So we get 0. We have 21 done. 22 is the same concepts. What do we have here? We have so what do we have? 20, 22 minus 14. So we do have an index of hydrogen deficiency of 4. Most possibly it's this right here, because you have 3 double bonds that get you to 3 plus the ring that gets you to 4. So most likely it's a benzene ring. Not for sure though, but most likely you'll select the one with the benzene ring. So 21 and 22 are done. Let's go on to 23 then. It says calculate the degrees of unsaturation. By now you should feel really comfortable with doing this. That 3 comes here. We're at minus 6 because there's 6 hydrogen divided by 2. So what is this? This is 6 plus 2 is 8, minus 6 is 2, so we get 1. So that means we could even have, okay, we have C3, so we could have this, or we could have this. So here's your ring, here's your double bond, that'd be 1 degree of unsaturation. So otherwise, if it was fully saturated, think about this. This would be Cn plus H2 plus 2N. I should put 2N plus 2, so this would be 3. 6, this would be 8. So we're missing 2 hydrogens, that's why it's unsaturated. So these are your 2 options. All right, so we did 23. All right, the last question of this homework set. Here it is. This is question 24. It says calculate the unsaturation number for each compound. Let me see. I'm just going to plug the numbers in, what we have. Let me do that. I got my calculator out. I don't need my calculator. What am I doing? So 10 plus 2 is 12. 4, 6, 3. I get 3 for the first one. I'll put it in there so you can see what I'm doing. And then what am I doing on this one? Yep. So 2 times 5 plus 2 minus 9 minus 0 plus 1 over 2. This is 10, 12, 3, 4, 2. You don't really need a calculator. We got 3 and 2. We got the right answers. And that's it. All right, do I have any questions? Okay, seeing no questions, you are free to go. We will continue on with chapter 15 NMR tomorrow. Have a great day.